Thank you. So now for something a little different. First off, I'm here to represent IGBP, the parent of Pages, and I'm pleased to say with 12 international projects, Pages being one, and a number of fast-track initiatives and other things that are under the IGBP umbrella, Pages is by far one of the best projects that you know, it's extremely product-driven. It nourishes its membership and its participants, and I'm really pleased to see the number of young people here, and so that's great. Go youth, go. Okay. So I'm going to tell you about something that might be an addition to the past emphasis on paleoclimate that Pages would like to get into in the next decade under Future Earth. And that is taking what it knows about paleoclimate and how to define it and put it in perspective with regard to global warming, and is that the footprint of humans is large, so large that it's more than just climate. And I think that Pages can play a very important role, and I want to try to show that or prove that with this presentation. The last couple of decades, Pages has been putting key global environmental parameters and trends into this Pleistocene-Holocene context. And it lays the foundation to the IPC reports over the last couple of decades on what humans are doing to the environment. But one major challenge is that the Holocene proxies are taking during the Anthropocene. And that's a problem. And we've heard about that earlier yesterday morning, and I want to emphasize it again, because humans have been altering not just the climate, but the chemistry, hydrology, snow cover, permafrost, and all of these other things that affect your proxies. So understanding this human footprint, I think, is a fundamental thing that Pages is contributing to and should continue to contribute to. If you were in the Holocene and we had no humans on Earth, then I think science is science, physics is physics, and we have a simple balance between, you know, how much is precipitating on the landscape, how much is evaporating, you know, what's the storage terms, what are the transients, to come up with how our floodplains and deltas would work. But we have a number of things that we have to address. The first one is, how can we predict the movement of water and sediment through the landscape? Turn off your cell phones. So most of the observations that we have made are in the 1960s to 1980s in terms of hydrology. And you heard a little bit about that from David's talk. And that's in this domain here. But that's a domain when we dammed much of the world's rivers already. In terms of water use, there's the 1960s to 1980s when we did our gauging. And again, we were already rapidly using water for all sorts of reasons, including irrigation. The total water consumption in millions of cubic meters per year is shown on this map. And you can see where blue is very high water use. This also is where most of the proxies that you've been showing the last day have come from, is in areas of large human footprint. And when we look at these graphs, these were produced on from the Dartmouth Flood Observatory. which now is under the Community Surface Dynamic Modeling System. They show magnitude 4 floods and magnitude 6 floods, and they show that the number of floods worldwide is increasing. And a lot of people have interpreted this as showing the intensification of the hydrological cycle. But we don't think that is the case. We actually think that many of the floods have to do with the human footprint rather than the intensification. So this is a classic diagram you may have seen. This is the stored water, stored runoff in percent for the world, where these dark colors show that you're storing more than 100% or 100% to all the way down to yellow being 2% of the water that would normally flow through the system. And so our world already is one where we store most of the water on the land surface in ways that are not natural. We do this for a wide variety of reasons, and I think you know most of them. Here's an example on the Aswan Dam where the interest is to increase the base flow so that you can grow crops on this delta 3 times a year. What you've done to increase that base flow is to reduce the floods. So you don't have floods anymore, but you have a larger base flow, and that's so typical. Here's a map from the Dartmouth Flood Observatory of the flooded area of the Chalfreya Delta, and the flood is 2011. And this is an enormous area, billions of dollars, loss of life. It was because of a precipitation event. So is that because of some sort of strong tropical monsoon that hit the area? In fact, it was because they had stored so much water from the previous year. Water is money to a dam operator, and so you want to have it in the bank. And then they realized the storm that was coming was so large that they had to release the water, and they released it, and they flooded all that area. So this is an example of one of the many floods where there's a human story behind. And there's just so many of these. So if you're looking at the paleo data, you would have to adjust, what was the cause of this flood? Is it really some hydrological event? Another thing we do is that we are using the water before it ever gets to the coastal sea. In the Indus, we have 108 units that enter the system, and only 45 of these units, and they're cubic kilometers of the units, get to the sea. Evaporation, diversion to fields, groundwater recharge, crop use, evapotranspiration, soil evaporation. So 50% of this, more than 50%, is gone before it gets to the sea. This is a diagram from a colleague of mine, John Milliman, where the red dots are greater than 30% of the flow that would normally hit the ocean doesn't hit the ocean. And it's used principally because of the agricultural needs of the area. You will see some green dots, and these green dots are because they're an increase in discharge because, at least in the US, we're taking water from the one side of the Rockies, moving it over to the other side where I live. So, but these consequences on discharge all have big impacts on biodiversity, salinization of soils, and coastal temperature and salinity changes. Another thing that humans have done that I think Pages is right to put into a perspective from the paleo is that the rivers once behaved like rivers. So this is a 700-kilometer floodplain of the Yellow Delta. And over time, this river migrated across this surface. And these are, from maps, these are where the main river system flowed across the 700-kilometer area. And this free-flowing back and forth is exactly what rivers should do. But in fact, sometime in the 15th century, the Chinese decided to not have this floodplain act as a floodplain anymore. And they spent 10 to 15% of their gross domestic product, which is a huge amount, putting in levees and repairing the levees every time there was a crevasse in the levees. And what happened is, and that's what you're looking at here, is that these rivers became super elevated. The levees trapped sediment that would otherwise have flown across the floodplain, and now you have this river system that's 10 to 20 meters higher than the floodplain. So that's not very natural. Colleagues from Japan and China, they put this together. This is the amount of sediment that historically would have come into these deltas a few thousand years ago. Let's say around 600 billion tons. And through agricultural use, deforestation, it shot up to something close to 2,200 billion tons. And now, because of dams, it's gone back down to 600 billion tons. So this is a cycle that we see again and again in rivers. So these 5 Asian rivers delivered an extra 2,000 gigatons of sediment above what they normally would have delivered to the landscape. And now this is strongly being reduced by dams. So the Mississippi River, before humans got to it, delivered about 430 million tons per year. This is a diagram of what it would have looked like in terms of increasing sediment load down the river. And in 1980 to 1990, it was only delivering 240 million tons per year, and now it's delivering around 120 million tons per year. And you will see that there are changes because of human use in the landscape. The Ohio River, which never delivered much sediment at all, now delivers a lot of sediment. And I want to show you my matrix moving. You're going to see this clock go by. This is from 1800 to the present. And you're going to see the placement of dams. Let me see if I can get operators. So you're going to see let's try it again. So the migration of Europeans across the country from the east to the west. These are dams. And I want to show you what they look like. So, if we look at this map, which is the placement, I'm going to show you a satellite image of that area where those dams are. All the water bodies you see here, those are the reservoirs. You see the Mississippi River coming down here. Everywhere else, those are dams. And if we blow up one of these areas, you can see the blue color is just showing where the suspended sediment is coming in, and you're trapping suspended sediment compared to the flood. And just so you see what it looks like on the giant globe, I should say that these are giant dams. These are dams, they're not like the last one that had all the dams. These are the ones that are only above 15 meters or higher in terms of dam height. And the red are showing the where the dams are being built. So you saw humanity's footprint on our surface. Let me just do that one more time. So you see the American and British Empire in India, Japan, Australia, some in Europe taking on. And I want you to pay attention to 1950 when Mao Zedong took over China. So here we go. So this leads, all of that leads to this one diagram. And this diagram is, so I worked with a colleague, Michel Maybeck, on finding pristine rivers. And we could hardly find any data on pristine rivers. And we wanted to calibrate a model. I guess at some level the model's not all that important. But the point is, we really had to get data from maybe 100 years ago. There may have only been a few years before a dam was put in. It was very difficult for us to get this data. And yes, you can see where post-dam is the Nile is down here. But if you took away the dam, this model works quite well in some of the other examples. Yes, there are Arctic pristine rivers, but those Arctic pristine rivers aren't really useful for developing proxies and dynamics that would impact, let's say, the tropical zone. So we did develop a model. It's called the Bogart model, but B-Q-A-R-T, and it's written out here. It deals with the amount of discharge, amount of area, the amount of relief and temperature in the drainage basin, and providing you a proxy of the suspended load delivered by a particular river. The model's not bad. It gets, on average, rivers about within plus or minus 38%. Some rivers it does not do well at all. So we've used this model to do a pre-Anthropocene, and we got 15.1 gigatons per year of suspended sediment. That's what's entering, or should have entered the ocean on a regular basis. And it has, for instance, glacial area, and of course, there's hardly any glacial area today. So this obviously would have had a big impact in the past, but little today. And it takes into account lithology and other factors. The model's not that important. What's important is that you really, to get the modern world right, you have to include this dam trapping, and you have to include the human erosion that's on the land surface. And now we've globally reduced to 12.8. That may not seem like we've done much, but the thing is, for many rivers, we've done orders of magnitude where we've increased it and decreased it, and they cancel out on a global basis. Here's the continents, here's the discharge, here's the with humans load, sediment load, and here's the before human sediment load. But I think you'll find more interesting individual rivers rather than big continents. So I've got a few rivers. And this was for a talk relating to deltas, and there's the U.S. Colorado, Ebro, Nile, Yellow, Indus. These are the percentage change in the mean discharge, the maximum discharge, the suspended load, and the sediment concentration. And there are some rivers that are someplace in between, and some rivers where the flow of water hasn't changed that much, but the sediment load has changed drastically. And we're getting to the point where we make predictions of global hydrology on a daily basis at a 10-kilometer grid around the world. And the only way we can do that is if we include all of these dynamics relating to dams. So this is the suspended load coming down the Nile, the Blue Nile, and it comes to the Aswan Dam. It deposits a lot of sediment, and so we have clean water that leaves the system. So let me summarize this part of the talk. So the Anthropocene activity both increases and, because of sequestration in reservoirs, decreases the sediment flux globally. The net effects tends to be a reduction in the sediment flux of large rivers. And these drivers are extremely complex. One story cannot be related to another river system that easily. So if you were looking at sea level, and I know Pages has played a role in placing sea level into perspective, I'm going to tell you a different perspective on sea level. A lot of people in the global change world have been interested in, used to see changes to the water volume of the ocean. And you melt glaciers, you withdraw water from ground, and you're going to increase the volume. You're going to add temperature, you're going to increase the volume sterically. But if you're interested in this bouncing ball, and you're one of the 500 million people that live on deltas, then you're also interested in whether you're getting sediment deposited, what the compaction rates are, and whether you're doing things to the system that are quite unusual. So if we look at this simple equation that are color-coded to these terms, natural conditions would say for a typical made-up delta that you would have 10 millimeters per year deposited. You would have not much of a sea level rise over the last few thousand years. Your natural rate of compaction, your accelerated compaction is 0 because there are no humans, and maybe your isostasy is about 2. And you get a delta that progrades and degrades. So on the anthropogenic side, you now have cut the amount of sediment in half. You've increased sea level rise due to our global warming impacts. And you now are creating this accelerated compaction side, and you get a sinking delta. If you look at the world deltas, on average, they're sinking 4 times faster than sea level is rising. You end up with deltas where there's, in Jakarta, 4 meters below sea level, 1974 to 2010. In Bangkok, Chao Phraya River, it's been settling at 10 centimeters per year, not 3 millimeters rising in sea level, but sinking at 10 centimeters, 100 millimeters. We understand some of the, using advanced techniques like differential INSAR and persistent scatterer INSAR, we're able to zone in on these deltas, look at why things are sinking. In the yellow delta, it's because of fish. They pump out so much water for these tonguefish, they have to they're very toxic excrements. And to get rid of it, they have to remove that every 10 days. And so they're just pumping this out. They're sinking this at 1 meter in 4 years. So if you're one of these billions of people living on deltas, you have a concern. I'm going to skip this to get to the last slide. So I think that Pages can play a very important role in putting the Anthropocene in perspective. It's big, and the human footprint is not just climate, as I showed in this talk. And the proxy techniques you use, the way you look at sediment records, and other records, tree rings we heard earlier, I think are just perfect for allowing you to have a viable position, not under IGBP, but under future Earth. So thank you.
Very much, James, for reminding us of the scale of the problem, and I guess there are questions.
thank you, Jim, for this talk. And you may have noticed that on Friday or Friday, I think I will give a talk which is along this line, but with a slightly different approach, based mostly on isotopic studies and things like that, and combining particulate fluxes with etc. One thing which puzzles me is, and then I would have perhaps a suggestion. One thing which puzzles me is how clearly can we constrain the rates of change? Okay. Because it's quite a critical issue. Not the pre-anthropogenic state versus the modern state, but the rate of change. Would you comment a little bit on that?
So do you have a particular parameter you want me to comment on?
You refer to particulate transport.
Okay.
In our case, okay. So that's, and I know that most of them are in Southeastern Asia, but there are many others. Okay.
Okay, so that's a very good question, and it's not an easy question to answer because most of these river systems are scale dependent. So large rivers, just like glaciers, large rivers respond very slowly, and therefore their rates of change are slower. It's even with the Amazon and all the deforestation that's gone on there, they've only been able to increase the sediment load by 12%. And it's a huge impact. I mean, it's like burning half of Canada, and it's only that's given the size of that river. So a very small river, you have that same deforestation like the Eel River in the US, and you can increase that within a day, a week, a month, you know, debris flows and things like that. So it's truly a difficult thing. You have to use scaling laws, scaling relationships to move towards an answer. You have to know the parameter and know the subject you're interested in. And it's great to see you, Hillary.
Well, maybe you give other persons also a chance and discuss it during the break. There was a question somewhere. Any more questions? Yes, here for you.
You have given the sediment budget mostly from the large rivers. But we have in India, if you look at the west coast of India, we have small rivers, mountain rivers. That means, you know, the sediment load comes immediately into the coastal seas. That budget we need to estimate for the total budgeting of the suspended load.
About the rivers on the western coast of India.
We have some data from the Mediterranean over further down the Nile River in the sea itself. And in our case, the response of the reduction in sediment going to the sea is immediately. So there is no delay. We worked on sediments, took short course, and we have a very rapid response.
For the rivers in the Mediterranean?
Not the rivers, the Nile itself. We are down current of the Nile. I'm from Israel, so we notice very rapid changes. In sediment.
Oh, downstream?
In the sea itself.
Yeah, downstream of the Aswan.
No, in the Mediterranean.
Oh yeah, well that makes sense because there it's where it's where these dams are located. And so if the dam is located close to the river mouth, then its impact would be much quicker than if the dam was placed further upstream.
Okay, final question, please.
In India, in West Coast, we have also observed that there is a blocking of sediments because if the river system, river inflow has been stopped, there is our dominance of tidal activity, and where most of the estuaries flow because of the tidal sediments. We have also observed in, say for example, Gulf of Cambay, there is all the mouth of the rivers has been choked. And that has led to form a new landform, and a tidal current has taken a dominant role rather than, so there is a change in a system, dominant system. As rivers were blocked, the tidal would change, and the landform building up has seen like putting up the Gulf away, I mean the retreating of the Gulf from the system.
Yeah, so that's a classic, so the question has to do with basically morphodynamics. So when The ocean has the ocean energy, whatever the energy in the ocean is, you know, whether it's tides or waves or some combination, currents. And if that energy wants to work on something, and if you give it the normal amount of sediment, it will develop some sort of stable system. But if you start to decrease or even increase the amount of sediment, then you will change the morphodynamics, definitely. Because that energy needs, if it doesn't have the sediment to work on, it'll just start eroding everything around.
Okay, thank you very much.